Here's what we're going to do today. We're going to get a little bit closer to reality today. Up until this point, whenever I give you something to do, I always give you most of the statistics that you need to solve the equation, right? So if I give you a problem, I give you the population mean, I give you the sample, I give you the standard deviation, right? It's all just given to you. And essentially up until this point, it's just plug and play. Like, okay, he's given me these three things, I get an equation, I plug them in, I do the math, and that's all it is. Well, with this section of the course, what we're going to do is, now that we have those fundamental principles that we understand, for example, what a normal distribution is, we can start playing with it a little bit. And what we're going to do today is say, well, what if there's something we don't know? Specifically, what if we don't know what the population mean is? Is there a way to figure it out given our sample? Now, when I say figure it out, I don't mean arrive at the exact number, because we can't necessarily do that. But based upon some of the tricks we've been doing with the normal curve, we can use a trick. And we can have an estimate of the population mean. So that's what we're going to do today. We're going to estimate a population mean given the sample mean that we have. And here's how we're going to do it. Here's an example. We love to know how much money people make, right? I mean, whether it's an athlete or a president or our colleagues, we just like to know how much money people make. You all are students, you hope to get a job soonish, and when you do that, you want to get a job that pays better, right? When we have lots of ideas about what effect an income has, and we talk about this a lot in politics, about the effect of income inequality. I gotta admit, I grew up, my dad grew up poor, and then he raised me like middle class, and now I'm like touching upon upper middle class, and it's a lot better. So there is a lot in society that we sort of value the idea of income and the opportunities that it affords, right? And even with my kid, I'm like, these are the jobs you need to get a step higher than me, right? So it's kind of like every parent wants their kids to make as much money as both of their parents make. So that's what I want Abby to do. I want Abby to get a job where she makes as much as mom and dad combined. Because that's what I do. I make more than my parents ever made combined. And that's our idea in America about sort of social mobility, right? So whether you're sociology or public health, the idea that having a higher income leads you to greater access to things like healthcare. If you're in comm or marketing and you want to sell people things, you got to figure out who target audiences are and what their incomes are. The West Wing television show that was on NBC for a number of years had the highest income level audience of any show. So if you're an advertiser and you know the people that watch West Wing make a lot of money, you will put ads out for things like Mercedes and not Walmart. Or if you're Target, you would advertise instead of Walmart. Right? They're two different audiences. So income is a variable that is important to lots of different fields. So here's a great example. 36 members of the Society of Industrial and Organizational Psychology. We call that IO Psych, reported their annual salary. So we have a sample of 36 people, and their average salary was $56,453. The standard deviation of this sample, which is the average difference from the mean, was 12,000. Does that seem like a lot? Does that seem like a good spread? Well, let's use the empirical rule. The empirical rule says about 68% are going to be plus or minus one standard deviation away. So 70% of our IO psych people are going to be between 44 and 68,000. That's a good spread, right? It's not ridiculous like some people, you know. This could be bigger, but it's still, you know, if you're on the -1, if you're still making 44,000, that's okay. What if we want to figure out what the population mean is for members of the IO society? How would we do that? Again, up until now, when I say we're going to talk about this, I've always done this, and what do I put in the middle? I put mu, right? I put the population mean there. But I don't know what that is. I got no clue. I do have a sample mean. I have X bar. So I've got one of the ticks, right? I've got one of the ticks that we usually measured away from the mean. So what could we do? Well, we're going to use an idea called a confidence interval. Confidence interval. An interval is a range of values. So we're going to take our single estimate, which is called a point estimate. Don't worry about that, right? 1 point. And we're going to say, all right, given that value that we've collected, let's create a confidence interval. So the range of value with a stated degree of confidence that should include the population mean. It should include the population mean. So are we really estimating what the population mean is? No. We're not really estimating what mu is, but what we're going to estimate is a range of values that we're pretty sure mu is in there somewhere. Make some sense? All right, let's work through a little bit more. All right. What do we want to do? Well, the first thing we have to do is we have to decide how big that range of values is going to be. And the way that I like to think about this is we've just got one sample, right? Of all of the IO psych people out there, we've got one sample of 36 people. We want to make it really likely that our sample mean would be in the range of values. Excuse me, I just misspoke. We want to be really sure that our population mean would be in the range of values that our sample gives us. How sure? Well, we're social scientists. We really like this idea of 95%. Right? So we're going to create a 95% confidence interval We are 95% confident that the interval that we create will contain that population mean. We're allowing for a little bit of error, but not a lot of error, just a little bit. If we generate a 100% confidence interval, it's going to be huge. And it's not going to provide us with much information. But a 95% confidence interval will be a little bit smaller. And we really want that confidence interval to contain that population mean. So this is how we do it. The confidence interval, it's actually two numbers. You have to do this equation twice. You do it twice because you're generating two values. One is a lower value. Another one is an upper value. The reason that you're going to generate, I've broken this out into two different equations because of this trick of the plus minus. I'm really not sure why we thought this was a good idea. Let's take two functions and put them right together. And then we'll just put it on one line, and you just have to remember that you have to do plus and minus. Again, if I get to fix math, one of the things I get to do is to say, well, instead of having one equation, let's just separate it into lowers and uppers. Now you'll notice a t there. That t could be a z as well, if our sample is large enough. One of the differences between t and z is how big your sample is. Okay, so we are going to use X bar, which is the mean that we have, 54,120 something. That's the mean from our sample. And we're going to add to it a unit of standard deviation. Actually, this is a standard error now. However far out we want our bounds to be. Now we know it's 95%. What do you think is the magical t, or excuse me, what is the magical z score for 95%? It's 1.96, right? We've memorized that. So if this if our sample were a lot bigger, this would actually turn into a z, and we would be using z scores. But because the potential for a sample to be small, we'll also learn it as having a t in there too. Yep. So if it's big, right, we know that the t distribution approximates a standard normal curve, and when you get big enough, your t turns into a z. Okay. So that's why I like the idea of learning it as a t, but in the back of your mind you have to just say, well, it could be a z too. All right. First thing we do, calculate the standard error. Now the standard error is like a standard deviation, but we have to take into account our sample size. So when you see S subscript X bar, now that should be a lot smaller, but I have to leave it a little bigger so you can actually read it off the slide. That's a subscript. S subscript X bar equals your standard deviation divided by the square root of n. In our study of IO Psych, the standard deviation was $12,000. Our sample was 36 people. Square root of 36 is 6, because 6 times 6 is 36. That's the square root. Take the standard deviation, divide it by that. Our standard error is $2,021. We're right on the border. And then when we look it up in the table, it'll probably be 1.96. Just to play it safe, let's just use T.
So does the type matter?
Yes. Because you should use T, because your sample is 9 people, and you plug in 1.96, you're going to get a wrong answer. So this is me being cautious. Yeah, about 30. I ran out of the T tables that I gave you all, but who has one here? Yeah, Chase's. I'll use Chase's. When you look at the T table that I gave you, it goes up to 38, and it is 2.024. And that's close to 1.96, but there's just little tiny degrees of difference. So again, playing it safe. All right. Next thing, degrees of freedom. Degrees of freedom are easy. N minus 1. We had 36 people. We have 35 degrees of freedom. We know our decision rule is going to set alpha as 0.05. That's the area in the tails. We're really looking for what the value number is for the 95% in the middle. So let's find the critical value of T. What with 0.025 in the tails and 35 degrees of freedom is our critical value of T? Yeah, it's not on that table. 2.042. There's that tricky plus or minus, right? Because it's a positive 2.042 to the right of the mean, and it's a negative to the left of the mean. So do the math. So here's the way that they do it. You just plug these numbers in. So we know what our sample mean is. That's the mean of the 36 IO Psych guys and gals. We've looked up T based upon the degrees of freedom. And they have a better chart than the one I handed out, which only has even numbers apparently. And then we plug in our standard error, which we've computed. Now the confidence interval, again, is two things. It is 56,453 plus 4,127. And it's also minus 4,127. So you have to pause and do it twice. And when you do that, you get the upper and the lower limits of the confidence interval. The lower limit is 52,325. The upper limit is 60,581. We can say with 95% confidence that the sample mean, sorry, damn it. We could say with 95% confidence that based upon our sample, we believe the population mean is between $52,000 and $60,000. It's pretty good, right? It's a lot better than using the empirical rule. That's what I said. There's a 0.95 probability that the interval contains the mean income for the population. There we go. It's better than nothing. We have a sample, but we recognize the limitations of our sample. Maybe our sample came from people, I don't know, in a geographic area. Maybe our sample of 36 people had more men than women, and men tend to be paid higher than women. For whatever reason, we're just going to say, listen, we have a sample. It's good size, 36 observations. We're pretty sure, 95% sure, that our sample, that the true population mean, the truth, is between these two numbers. We're able to do that because of the normal curve. So we have our normal curve. We go out 1.96 standard errors from each side. And if we were to repeat this, if we were to do another sample, another 36 people, and another 36 people, and 40 people, right? If we go out and we get another 99 samples, of those 99 samples, plus the one we did first, so of our 100 samples, 95% of those sample means should also be in that range. Last week, when we started doing a little bit of hypothesis testing, we were testing, is it weird that our sample mean is outside of that 95%? Right? So we were saying, well, if the population's mean is this, and we know what the population mean is, and our group is way out here, isn't that odd? Well, yeah, it's odd, because you're way out here. You're way in the tails. You are different. So doing that reading program that increased your words per minute by 50 words per minute, you are different than the kids that didn't have the reading program. Anybody in here related to a mortician? Because I used this example in the Tuesday class, and I had a student whose dad was a mortician, and I felt like a jerk. Sorry, if you're listening. There's an example that in the book that draws upon a study of students who are interested in mortuary sciences. And I think the question is, are they, I don't want to say, they don't avoid social interaction, but social interaction is less important to them. And Are those people truly different from the population? Are they out here in the tails? So we were already doing this, right? We were saying, well, how likely are we to get our sample mean given what we know about the population? Now we're just sort of doing this in reverse. We have a sample mean. We can infer a range of values for that population mean, and 95% of our future samples should fall within this range. So we're just taking the logic that we already had and reversing it. If we know what the population mean is, then we should know if our sample is outside of the 95% confidence interval for that population. So if we get a sample, we can then generate a 95% confidence interval, and all 95% of all future samples should be within that range. Same exact curve, same exact shaded region. All we're doing now is saying, all right, this is the inventory of what we have. Given what we have, what else can we infer? What else can we deduce? This is inferential statistics. What else can we, I almost said no, think, given the data we observed? One more way to think about these confidence intervals. Remember, I said, well, we can just keep collecting samples, right? Collect 100 samples, 95 of them should generate the sample mean should fall within 95% of the population mean. That was the last way to think about it. This one takes this and spins it slightly another way. When we generate all of those samples, there might be some whose confidence interval does not contain the population mean. Why is that? Okay. Why is that? Why? But why? In fact, I can pretty much guarantee that if we did this 100 times, we will get some that don't contain the true sample mean or population mean. Why is that? Well, what is our decision rule? Is it 100% confidence? No, it's 95, which leaves 5% for we're going to have some errors. This is the one question that you get wrong on the test, but you still get an A. It's going to happen. You're going to get a sample that looks nothing like the population. This 205 class last fall had an irrational hatred for Hillary Clinton. I had a feeling thermometer score. Feeling thermometer is when you ask somebody to rate them between 0 and 100. And if you like them, then they're hot and you give them a high score, and if you don't like them, you say they're cold and you give them a low score. The average from a much larger sample in the national election study was something like 68 for Hillary. In my class was like 20. They were the ones that were way over here in the tails. And we worked through the example, and I'm like, you guys are that 5%. You are the one sample that falls outside of the confidence interval. Good job. Thanks for doing that. And then I never tried to do that again because I knew that these guys are just a little bit different than the population. Way to kill a class exercise, everybody. It would sort of be like the same thing if I was doing the shoe size example with the men's basketball team. So if my question, because I work for Nike, is what's the average shoe size, and I can't measure every person's foot in the world, But I can go out and collect a bunch of samples and get sample means, and I can create confidence intervals around those sample means. Well, if one of my samples is the men's basketball team, and they're all wearing like size 19 shoes, they're going to be that one sample that's outside of the population mean. We okay with this? Are you okay with this?
Yeah, there's a lot coming out.
Anybody not okay with this? Jeff, we all right?
The only question I had was curious about like the 30 people in the population size, like why we switch charts from
Okay, well, that's my fault.
So I don't quite get how you're supposed to find T and calculate the freedom. Well,
Okay.
freedom is just number minus.
So for you guys, because for you guys, I didn't spend a whole day on the T distribution, let me just do a reminder. Okay, so we have this thing called the T distribution. It's like a normal, but we designed it for if we don't have a large number of observations. And so what it allows to do, you can't really tell from this, but what we really have is we have a normal that's been pushed down. And so the tails, they're a lot fatter. Kind of like when your hair gets too long and it swoops out. At least that's what it does on my head. It's got a little extra curve to it. A little extra in the tails. All right, so if you look at this is a little extra here in this tail. That's the T distribution. Now, one of the things about the T distribution is, as the sample size gets bigger, it gets taller. It gets more like a normal curve. So on the T table, what we have here is we have those critical values. Because with the T table, we know, right? We want 1.9, or we want 95% confidence. That's the middle column. But it's saying, listen, when your n is small and those curves are a little thicker, that value of T gets higher because you go out a little bit more. Because again, it's smushed out. So depending upon our sample size, which in this table is reflected by degrees of freedom, we're calculating one statistic. So we always take one away from our degrees of freedom. So that's why degrees of freedom is n minus 1. So if our sample was 11 individuals, 11, I use you here in the room as my sample, I would have how many degrees of freedom? 10. And with 10 degrees of freedom, the value of T that gives me 95% is 2.228. And so that's where that value of T comes from. Well, as I was saying, because of the central limit theorem, right, as n approaches infinity, our value gets closer and closer to the magical number we all have memorized of 1.96. And then at any point, it doesn't matter. You keep adding observations, it doesn't help you because you are now actually a normal curve. You're no longer approximating a normal curve. You are a normal curve. Does that clear that up?
Yeah.
Just because I didn't get enough with the T distribution in you guys. And that's why I say it's okay to play it safe and in the equations use the T. Because if you start in your mind, okay, T, and then you go, oh wait, I have an n of 72. Well, if I have an n of 72, how many degrees of freedom do I have? It's just as if I have an infinite amount, right? I'm already at 1.96. Light bulb?
Yeah.
All right. Whew. It took us a little bit, but we got there. The confidence interval is the one thing that people misunderstand the most of all of this. And what does the confidence interval actually give us? We are getting the probability that the confidence interval contains the population mean. So this interval, 95% chance that the population mean is in this interval. Not the probability that the population mean is in the interval, which makes no sense to me. It's doublespeak. Probability that the confidence interval contains the population mean, not the probability that the population mean is in the interval. I don't understand how that's different.
Is that different?
It is, actually. I'm lying. I do understand. Probability that the confidence interval contains the population mean. So it's the probability that the confidence interval crosses that little line that comes down. So it's about the probability of the location of the interval relative to the mean. But it is not the probability that the mean is in the interval. That we're actually sort of saying our interval goes, boop, there it is. It has taken me about, I don't know, 20 years to get this, and then I lose it. It's just one of those things where you're like, okay, but why not? Right? Why not that this interval contains the mean versus the mean is in the interval? Like, how is that different? It has to do with what it is you're putting, right? What is the focus? Is the focus on placing the population mean? No. The focus is on placing the confidence interval over the population mean. So you're putting one on top of the other versus putting one in the other. Whatever. Like I said, for about 20 years I didn't understand this, and I did just fine. Because it's a really tiny argument. But it's the one thing that you can be talking about it, and somebody who knows and somebody who it bothers, immediately they're like, oh, you're stupid. And it's a sort of superficial thing. I got two things in the English language that I hate. One is when you write the word thing. You can say the word thing, but you can't write the word thing. Because when you're writing, you're taking your time, and you should actually use the word that's appropriate. Now, if I'm talking quickly, I can say I hate two things about the English language, because I'm talking fast. So I hate that. I also believe in the Harvard or the Oxford, or whatever you want to call it, the extra comma. Till I die. Put the extra comma in. But does that make me does it make the university, which in its publications follows a style guide which says you don't use the Oxford comma, does that make Coastal stupid? No. Can I rant and rave about it? Absolutely. Confidence intervals are that thing that you, see, that thing, that concept that you can think you have, but if you just say it slightly off, people are going to be like, you don't know what you're talking about. So what I tell you is stick to a script. Stick to a script, and when you talk about confidence intervals, look it up in a book and go, this is what the book says. According to Howard here, a confidence interval means, and then you restate it how Howard states it. So we have, let's see, this little paragraph here. There is a 95% probability that the interval contains the mean income for the population. Just say it like that. That the interval is on the mean, not that the mean is in the interval. Remember? The interval is on the mean. Even then, if you squint too hard at that, you'll go, wait a minute, he's still wrong. Don't worry about it. Okay? If you know, the book, we don't need to spend a lot of time on this. It depends on what you know, which equation you use. So if you're given a set of information, you sort of look and go, well, I have these three parts, so I use this equation. There is another equation, and the difference is if we know what the population standard error is, or the population standard deviation. It's the exact same equation, except we substitute z for t. Nope, you don't need to. Here's why. Remember, what we're doing is thinking about how far away we are from the mean in variance units, right? So a z-score is just a unit of standard deviation. If I know what the population standard deviation is, I'm 1.96 units away. I don't know what the mean is, but I know how far away it is from the mean. Which raises the question, how the hell did you compute the population standard error and not know what the population mean was? Because don't you have to do x minus x bar squared? Like, this is one of those situations where I'm like, you are overthinking this, people. Because I'm pretty sure to get this little sigma, you had to know what sigma was. And when we look at the thing for sigma, pretty sure that you're going to find a mu in there. But there are evil stats professors out there. And they know what mu is, but they don't want to tell you. So they hide it from you. And they say, calculate the standard, calculate the confidence interval. Go. And they're just going to hold it back and not tell you. That's the only reason I can think about this. Why it would be that way. But if you look at it, same thing, right? Our sample mean plus minus how far away we are. This is all the same. Population standard error is the same thing as the sample standard error. It's your measure of standard deviation divided by square root of n. Again, we're adjusting for the actual sample size. Plus or minus 1.96 because it's a z. So what matters when we're doing this? Two things matter. The sample size. Why? Why does the sample size matter? You know.
It has to be like large enough to assume it's like normal.
Not, it has to be large enough, but what about the size? As our sample gets larger, what happens? It comes closer to the population. Yep. And that's called the, or the idea behind it is the central limit theorem. So our sample size is going to be important. Functionally, sample size is important when we're determining whether to use T or Z. In reality, it's also important because larger our sample size, the closer our mean is going to be to the population mean. And also, the smaller that interval is going to get. Because remember, sample size is part of the denominator in the standard error, and the standard error gets smaller as the population size goes up. Okay. The other part about the size of the confidence interval is how much confidence you want to have. So what value of Z you pick is based off of what you've set your decision rule at. So if you say 95%, then you're going to use the Z-score for 5% in the tails. But if you use 90%, then that Z-score is going to be smaller, and then your confidence interval is also going to be smaller. So larger the sample size, the narrower the confidence interval. Narrower is better. Sorry, I misspoke about that. If you really wanted to get into the weeds, like really, 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 and I'm not going to ask you to do this ever, there is a way to figure out how big you want your sample to be, or you need your sample to be. You can estimate the sample size needed to get the desired width. This is rare. I don't think I've ever used this, but it's possible. So you can sort of reverse engineer this and say, how big of a sample do I have to get to be within $2,000 of what the population mean actually is? You want to have a very small confidence interval. You can do that. I'm not going to do this. I'm not going to waste time on it. It's possible. Factors affecting the size. So would you rather be more certain that a given interval contains the mean, or would you rather be more precise? Also, yeah, there we go. No. This is true. Rather than make a decision about significance, researchers could use the confidence interval for the mean to estimate. You could do that, but we don't do a lot of that. All right. So that's confidence intervals. We're estimating where mu is based upon our sample. And 95% of the time, we get our bar on the right spot. Now I'm confused again. I'm still not sure how that's not putting the mean in the bar, but whatever. Just think of it as the bar's on the right spot. It's kind of like pin the tail on the donkey, right? Everybody go out and get a sample and come back and place it on the thing. And then I'll reveal to you where the sample mean was. Most of you will get it. Not all of you, though, because you'll wander into the men's locker room.